Maarten,
Alex,
Marlies van der Wijsvaart,
Mari,
Willeke,
Laurent,
Nika,
and Jake.
we're the organizers of the Astronomy Untitled Groningen.
We have our events every first Monday of the month at the Burtscher Cafe in Groningen.
Our events are sponsored by our institutes.
The Kaptein Astronomical Institute of the University of Groningen.
Netherlands Institute for Radio Astronomy.
and Netherlands Institute for Space Research.
and don't forget to follow us on our social media.
Hi, everybody. Welcome to Astronomy on Tap Groningen. I'm Nika Jurlin, and I will co-host today's event with Jake. So first off, this is our second live. So in our first live, what we did is answer your questions. And those are the questions you asked us on social media. So we answered those questions in the form of little videos that we streamed last month. In case you missed it, but would like to have a look, you can see it on our YouTube or on our Facebook. Today, we return to what we used to do before in the Burtscher Cafe. So we have two speakers, and these two speakers will talk about the Earth. So we decided to have this special edition on Earth because recently on the 22nd of April, we celebrated the Earth Day. So during these questions or after them, we would like to ask you to ask questions. You can do so either in the comment of this video, or you can also do it on Facebook, YouTube, or any of the social media. But if you do it on Instagram or Twitter, just tag us so that we are sure to receive these questions. So after these two speakers, we will have a short break, and just to get you ready for the quiz. So in the pub quiz, we will have only one session. So unlike when we have it live, when we have 3 sessions, we will just have the one that is related to our speakers' talks. So first off, we start with Dr. Leo Burtscher. He's an astronomer from Germany, and he finished his PhD and also his postdoc in Germany, studying mostly active galactic nuclei. Then he moved to Leiden, where he holds a permanent position. So he's a staff astronomer at Leiden Observatory, and he's also calibration scientist for METIS, which is an instrument for the extremely large telescope. Today, Leo will talk about astronomical climate lies.
All right, I suppose people can see and hear me, at least I hope. So, hello, let me now start sharing my entire screen. And I'll move to my presentation. Okay, so this talk is titled Astronomical Climate Lies, and it came essentially as a, well, as always, or as often, a talk that I just wanted to do because I wanted to know how many astronomical factors are actually involved in the changing climate that we see. Of course, I know the answer, and I hope all of you know as well, that astronomical factors are not the reason for the climate crisis that we have. But nevertheless, it's actually quite interesting from an astronomical and climate point of view to study what factors there are. So in this talk, I'll cover first a little bit about the habitable zones that you may have heard in the context perhaps of exoplanets. This is kind of a broad introduction of what is our cosmic environment and what does it mean for complex life. And then we go to two main factors that have a big influence actually on the Earth's climate, although, and I will repeat this many times, not on the climate crisis. And that's our solar system, or the sun, more specifically. So what influence the solar radiation has on our climate. And then our orbit around the sun. So that's the Earth orbital parameters. And then I'll end with a little summary of what relation there is to the climate crisis. All right, so let's start with some real astronomy. So there are places in the universe where complex life can develop, and others, most places actually, where this is probably not possible. The exact details of all of this, of course, are still very much unknown. There is, since only really a few years, this study of astrobiology has taken off quite a lot, of course, with the discovery of exoplanets, which received the Nobel Prize just 2 years ago or so. Now we know something like 4,000 exoplanets, but we know none yet that are really, that host life. We know a couple that might host life, but none that really do, except our own, of course, which is not an exoplanet, strictly. So we can ask for what factors are probably involved in making a place suitable for complex life. And the term complex life really comes from a book that I can quite recommend to read, which is called Rare Earth. And that book essentially tells the story of why Earth is so special and why it's quite likely that we are the only ones who are, we are the only complex life in our galaxy, because there are so many factors that need to get together. And the authors argue that simple life, like, I don't know, some microbe or so, might exist in many places, but complex life, which means, as we know, an evolution that lasts over really many, many millions of years until something like us exists, requires not just favorable conditions for life in a short amount of time, but stable, favorable conditions over many, many million years. And for that, our Milky Way is actually, and especially our solar system, is actually quite special. So our galaxy, the galaxy in which we live, first of all, is a galaxy with little nuclear activity. So the black hole that you probably know about in the center of our Milky Way, about 4 million solar masses, heavy, is not very active. I mean, from time to time, it swallows something like a couple of comets, or some larger pieces that are perhaps a few Earth masses large, but nothing really substantial. So it doesn't produce giant jets or huge energy outbreaks like is seen in a few other galaxies, at least currently not. That might have been different many years ago, 6 million years ago, for example. There might have been an outbreak, but that didn't reach us. And that's the second point here, because our location is relatively far away from the central region where energetic phenomena happen also besides from the black hole, just because you have a lot of stars. But it's also not too far away, so we have enough material still so that planets can actually exist. And then finally, we live in a relatively quiet neighborhood, the so-called local bubble, where several supernovae went off a long time ago. And so now not much is happening there. It's actually an underdense region where the sun is living in the center, in the surrounding of some parsecs. And so that might also be favorable for life. then the next habitable zone that there is the habitable zone around the star. And so this is a picture that I took from the ESO webpage when another exoplanet just had been discovered, in this case Gliese 518. But this is mostly actually to illustrate our solar system. So you can see the inner 4 rocky planets and Jupiter here, and the sun, and you can see this band here, this light band, which indicates at what distance from the sun essentially liquid water exists on the surface. And this is known as the habitable zone, and we are of course in that. You can see that we're perhaps a bit closer to the hot end, so to say, than to the cold end, but still we're quite nicely in there. And there's a couple of other factors that make our solar system, our sun, very favorable for life. So our sun is relatively quiet. There has actually just been research a few weeks ago that said that compared our sun with similar stars, so-called solar type stars in our neighborhood, and they found that our sun was really extraordinarily boring, let's say. So it doesn't do a lot, which is good for life. So it doesn't have major outbreaks, magnetic activity and stuff. It has it a little bit, of course, but by far not as much as other stars. And there are further factors, which I think I won't go into here, but we can discuss this later, like the moon, which stabilizes the Earth orbit, and Jupiter, which keeps away asteroids. So a number of factors that make this quite nice. All right, okay, so this is the big picture of the environment in which we live. And these are, of course, all factors that are essentially stable for, well, timescales of thousands of years, except 2, and that's the solar activity and the Earth orbit. And those are the ones I want to discuss now more. So you might know that the sun has an activity cycle of 11 years, or very exactly, actually 22 years, but that's just because the magnetic field rotates. It's once here, and then it rotates this way, and then here, and you can see this as the 11-year cycle, and then it rotates further, but the second 11-year cycle is more or less has the same phenomena as the first cycle. And so this is these are some pictures of the sun where you can see the range of activities that is typically observed from a very active sun, let's say in the lower left, and then it goes to a less active sun, and then it becomes more active again. And so at the moment, actually, we're, you can see in this graph here in 2020, we're really at the minimum of a solar cycle between so-called cycles 24 and 25. And not a lot is happening. So if you went out with proper solar protecting filters, of course, and observed the sun, you would likely not see an image like in the lower right with a lot of sunspots, as you can see here, but you would likely see a solar disk, yellow or whatever your filter gives you, with probably not a lot happening out there. But this wasn't always the case. So the sun is sometimes more active, and there's also longer term cycles in the sun. And one of these cycles actually led to one of these cycles is connected, I should say, to a cold period, at least in Europe. And this cold period has been described by many people, but most nicely, I think, depicted here on this picture by Hendrik Averkamp, which you can see in the Rijksmuseum. Well, not at the moment, of course, because it's also closed, but you can see it online also, the Rijksmuseum.nl. It's called Winterlandschap met ijsvermaak, so winter landscape with happy time on the ice. And at this time, 1608, it was actually unusually cold in Europe. As you might also know, this is actually 1 year before Galileo pointed his telescope to the stars for the first time. So you can ask now, okay, how do we know what the solar activity was at that time? And with this, I'd like to introduce you to so-called proxies, which is a difficult topic that is also not my specialty, of course, but it's in this case actually quite easy to understand. So this is the solar activity that has been reconstructed for the last more than 1,000 years based on measurements of carbon-14. So you might know that carbon, one of the most frequent elements in the Earth crust, comes with 2 natural so-called isotopes. So one has 12 atoms, that's the normal carbon. One has 13 atoms. And then there is a radioactive version of it called C14 that has 2 extra neutrons compared to the normal carbon. And it decays in about 6,000 years into nitrogen. And you can measure, and this radioactive carbon is produced by cosmic rays that come mostly from the sun. So you can then deduce that the presence of this atom, or the deviation of the number of these atoms compared to the long-term average, depends on the cosmic rays that hit the Earth, and that again is an indicator for solar activity. Now, how exactly that is produced and calibrated, I actually have a second slide on that, but we can do this in the discussion in case you really want to know. But let's just look at this plot here. So you can see here the deviation of this specific carbon atom. So let's call this now just the solar activity as a function of time. And you can see that between, let's say, 1400 and 1800 or so, there was, kind of a little dip in the solar activity. And this indeed coincides with what is known as the Little Ice Age. So this is roughly when Hendrik Averkamp made his picture in 1608. And that actually led to a lot of speculation that this reduced activity of the sun might be connected with the so-called Little Ice Age. This is by far not proven. I mean, it's an interesting possibility, but there are other effects as well that might play a role. One is orbital cycles that we discuss in just a few minutes. Another one is volcanic activity. So it is known that if a lot of volcanoes erupt, they produce lots of dust, and this dust increases the albedo of the Earth. So it deflects more sunlight, and it leads to less heating of the Earth essentially, and that produces more ice, and then you have actually a feedback cycle that goes into an ice age. All right, so is it then the sun's fault that our climate is heating up now? Well, this question can be very clearly answered with a no, and it is studied in quite some detail. There has been many years ago various people who claimed that it was the sun. They often then like to show this graph only until about 1960, where it almost looks like a correlation. But if you look at the more recent time, then you can clearly see that there is this temperature deviation starting in the 1970s very clearly, and has reached now something like 1 degree above the so-called pre-industrial time. And you can see the solar activity, which is actually measured based on the sunspots since for the last 100 years, or more than several hundred years actually, or from these proxies. And you can see that there is no correlation between these two. So the sun is not the culprit. Fortunately, unfortunately, well, we can discuss this, but at least it's not the sun that's causing this deviation in temperature. Now, if we go a little bit further back in time, we can look at the temperature variations over the last thousands of years. And this is done with another so-called proxy, so another measurement that you can easily get, or that you can get over this long time scale. In this case, it's the deviation of again, a specific isotope, so a specific variant, let's say, of the atom oxygen. And there's one called 18, oxygen 18. It's a little bit heavier than the normal oxygen, so it's more likely to be in ice than in the air. And indeed, this this isotope is then used as an indication for temperature, actually, because if more of this is found in the ice cores, then that means there is more a higher fraction of water that is bound in ice. And if you look back here and then you look at, okay, how many cycles do I have and how often do these cycles appear, you see that it's roughly every 100,000 years, so 0.01, 1 in 100 cycles per 1,000 years, so 100,000 year is roughly the cycle that we see. And indeed, over the last several million years, every 100,000 years we had an ice age. And that's at least interesting to say, oh, why is that actually? And there's a number of reasons why that could be. And a Serbian geologist, astronomer, discovered them for the first time. We mentioned him just later, Willebrands Milankovic. And I'll just point out 4 possible effects. So one is called orbital eccentricity. That just means that the sun isn't, or the Earth isn't exactly circulating around the sun in a circle, but it has an ellipse. and the eccentricity of this ellipse is changing over time a little bit. Another one is the tilt, you know, the 23.5 degree that we have now, that changes also over time. That's the one that produces summer and winter, it is variable with time. Another one is the precession of the apsides. Sounds very difficult, but you can see here in the image what it does. So the point closest to the sun is so if you take this fixed, then the ellipse of the Earth orbit is rotating around the sun. And the last one, this is a complicated picture, but it's actually still easy to understand, is the inclination of the orbit. So if you think of a reference plane, which is essentially all other planets, or mostly Jupiter actually, who is the most massive, the one with the most angular momentum, you take that one and you look at the Earth orbit. This is the greenish plane here. Then there's an inclination between these two, and this inclination changes with time. And then if you look at which of these factors has this 100,000 year cycle, the one that wins is actually the inclination. And this is relatively recent research. So this has, this has for a long time, there have been discussions over what really is the dominant effect here. But yeah, it seems it's inclination that causes this shift every 100,000 years. And as I said, this has been described already more than 100 years ago, actually during the First World War, by Milutin Milankovic, who studied this. He didn't know at the time that it was inclination, but he named a number of effects that could be it. And the possible reason is also interesting. So in this paper that is cited here on the side, they say that this might have to do with the Earth orbit crossing a plane where you have lots of debris from comets. So think of like an meteoroid shower that you have in the summer, for example, the Perseids or so, but then in a massive way, where you have so many of these meteoroids or comets that hit the Earth's atmosphere, that you really get again this cycle, like in volcanoes, that you have more extinction, and then you have more ice, and then you have even more albedo due to the ice, and then it gets really cold. All right, so that brings me close to the end, or at least to the last point, namely to the question, what is then the climate crisis, and is there any relation? I already took it away, but I think it's still interesting to see this drastic difference in effects. So the changes we looked at were hundreds of thousands of years, the axis that you can see here, you can see the ice ages. And this is, in this plot, just the CO2 concentration, which also changes during the ice age cycles. Well, that's a different topic. But you can see here that the change that we have observed in the last 50, 100 years or so is really dramatic. And it has reached levels that are far, far higher than anything that we have seen over the last hundreds of thousands of years. And a very nice depiction of this effect is actually done in this comic that I can highly recommend to read in full. I just have a few snippets here, and you see the link in the bottom. So this is by Randall Munro, the maker of XKCD, a really nice physics comics, but these are comics that are really meant to explain physics for everyone. So then this is really very nice to read. And he has this huge comic that you can see the scale here. It starts at 20,000 years before our time, and it goes in 500-year blocks down. And you can see the dotted line here is the temperature on Earth. And indeed, 20,000 years ago, it was a bit colder. Then it rised, and then we have the so-called medieval warm time, and then it stayed very, very, very constant over a long time. And then now we suddenly have this increase here, that this is 2016. It has, of course, continued in the last 4 years. That is really unprecedented over the last really many 10,000, 100,000 of years. Actually never seen before that there is such a really fast increase. Of course, you can also have this in a little more scientific way. This is the kind of the summary of what we know about the Earth's climate over the last 100 years or so. You can see in different colors and in black, actually in black, red, and green, the observed temperature curves for the global mean temperature, which is a difficult thing actually to estimate. So there's different projects that do this. And you can see that that these different estimates actually agree very well with each other. And you can also see this clear deviation since 50 years or so, that you have this increase in temperature. So this is now in degree Fahrenheit, so that's why it's more than 1 degree, in case you wonder. And you can see in blue, in thick blue, what they call here natural forcing. So this is everything that you expect from external factors, and that includes these astronomical factors like orbital changes and solar radiation. And you can see that these have a very, very minor effect, and actually in some cases even a negative effect. So they can before not explain what we are seeing. Yeah, and this is really close to the end then. So then the question is, can astronomy do something to solve the climate crisis? And this is going to be answered in the second talk by Michele just afterwards. So stay tuned. If the astronomical factors have nothing to do with the climate, can astronomy still do something? We will see. Okay, so this is my summary with 3 take-home points. The astronomical environment determines much about the habitability. So we know that in many places, like in this beautiful galaxy that you can see here in the backdrop, Centaurus A, it's probably not a nice place to live, because we have in some galaxies massive outbursts of radiation, particles bombarding planets, or just lots of stars exploding. So the atmosphere, the astronomical environment has a big impact on how livable a planet is. But the timescales that we observe in the climate crisis are on a very different scale. So this is really hundreds of years, whereas astronomical scales are more likely tens of thousands or millions of years. Yeah, and then this is really the conclusion that I want to convey here, that all these other factors are, I think, quite interesting to study, what might have caused the ice ages, but it is not a reason for what we see right now. So the climate crisis that we have is really our climate crisis, and we need to solve it ourselves. Thank you.
Thank you, Leo. So it was very interesting talk and very interesting summary, because I think there is so many things that we can say on this topic. So first off, there is a question: do we know when the next major ice age will be?
I think the true answer is probably no. But I mean, based on these, well, should I share my screen again? Based on these cycles, we are actually in a in one of these in the end of these inter ice age regimes, and I think the next cycle for cooling down might then perhaps expected to be in some 10,000 years. But there are different cycles at play. So the 100,000 cycle that I pointed out is just one cycle. There's also a 40,000 year cycle possibly, but that is a bit more difficult to relate to astronomy. I think, yeah, since we don't really know what's causing these cycles, it's hard. It's hard to make a clear prediction of when the next one will be. Yeah. But I wouldn't hold my breath for it.
Okay. Then we have the second question, that is, what would happen if there was no moon? How would the orbit change?
Oh, the orbit of the Earth would not change as far as I know, but the axis of the Earth, the spin axis of the Earth would be less stable. So you might not have this small change that I showed in inclination between whatever 22 and 24 degrees, but it might change much more, and perhaps even flip over, like we see in other planets. And then, of course, the long-term stability of the climate is gone. And that means that complex life has a harder time to evolve.
Okay. The second question is third question, is there any solar ice age coming up soon? So, well, we actually answered that one with the first question.
Yeah, I guess we don't even know if the sun has ever produced an ice age.
Yeah, yeah.
The little ice age that, by the way, was really only seen in the northern hemisphere. So it was not a global temperature change like the one that we observe right now. I mean, the sun is relatively quiet at the moment, but then these 11-year cycles are something different anyway. So again, also here, I think there's no real evidence that the sun is causing any climate changes over the last hundreds of years. I mean, there might be a tiny factor, but the much major factor, much larger factor that we see is really what we are doing.
Then we have a question. The periodicity of ice age is due to relative difference in 14C atoms, which is due to cosmic rays. Does this infer that some intensity of cosmic rays follows some periodicity, or is it somehow related to the solar cycle?
Yeah, so the cosmic rays are cosmic rays produce these radioactive isotopes of carbon, and the major source of cosmic rays at Earth is the sun. So that's why so it's a very indirect argument, you can say, but you can say, okay, we have C14, which we can measure relatively easily, the radiocarbon method. We know it's caused mostly, not entirely, can also, a tiny amount can also be due to lightning, for example, but mostly it's caused due to cosmic rays, and cosmic rays mostly come from the sun. So there's always a 90% factor or so. There's also cosmic rays that come from outside our galaxy, but these are very few. So mostly it's really related to the sun in that case.
Okay, so we have one more that we will read, but then we will continue. So can we make predictions on how these astronomical influences will further influence the trend that's followed now due to the anthropogenic emissions?
I'm not quite sure I understand the question fully. So the anthropogenic emissions are really, well, that's at least the message I'm trying to convey here, that they're really something completely different. They happen on a much shorter time scale, and they are anthropogenic, so we produce them.
Yeah.
And you would need to have a massive astronomical factor that's kind of counterbalancing them, like, I don't know, some weird change in orbit that produces an ice age, and then perhaps these things would balance out. But that's very speculative, and there's no sign of that happening. So what we want is astronomically a very simple and stable climate, and then we just need to make sure that we don't mess it up.
Yeah, so humans always. Okay, well, I would like to actually read one more. Just are we able to observe climate changes on other planets?
Yeah, that's a very good question. I'm not sure if there's enough time evidence that that we can see it happening live, like on Earth. But there is evidence that, for example, on Mars, there used to be water. There are these river-like phenomena where you think, okay, perhaps there was water in the past. And also on Venus, as far as I know, but perhaps someone else would like to chime in here because I'm not really a planetary expert. Yeah. Also on Venus, people say that there might have been a runaway climate crisis. So this is not expected to happen on Earth in such a dramatic way, not even in the worst case scenario. But in principle, if you add up all these tipping points, so you have more methane emission, getting an even stronger climate effect, and then you have the ice caps melting off that reduces your albedo, and you get even more heating. And so there are a couple of these points on Earth, and they might have also been on Venus and produced the very hostile effects that we see there. But I think in real time, I don't think this has been observed in real time. So this is really from fossil record. And for exoplanets, well, we have a hard time to observe any atmospheric information at all. So people are very happy since, I don't know, 10, 20 years or so to actually say, oh, there might be some oxygen in the atmosphere. And by far not say if there are changes on still relatively small levels. So that is something to come, but not yet.
Yeah, also with some new instruments.
Yes, of course. I can make some advertisement for Metis, which of course will hopefully be able to measure and characterize the atmosphere of a couple of Earth-like planets, actually. So one of the biggest discovery that we hope to make is to take an image and a spectrum of planets orbiting the nearest stellar system, Alpha Centauri, with Proxima Centauri in it, And there we would be able to see various tracers for elements and atoms and molecules that could tell us whether there is life or could be life on these planets. Yeah.
Well, okay, that's a new title then for the new talk. But also, so I wanted to say that that anybody can join us also after these sessions and also after the pub quiz. We will open the Zoom session so that you can also join in and you can ask questions about also extremely large telescope and whatever you would like to additionally know. So yeah, let's clap in our homes for Leo.
Thanks. Looking forward to see you online later.
So next off, we will have Michelle Willebrands. So Michelle did her bachelor's in astronomy, and she also did her master's in astronomy, but also in science communication in Leiden. Then she went to South Africa. She did an internship there, and she discovered astronomy for development. So currently, she's coordinating the International Astronomical Union European Regional Office of Astronomy for Development. And today she will talk to us about cherishing the pale blue dot. Here you go, Michelle.
All right, let me share my screen here. Okay. Right, so where Leo was talking about the scientific background of the climate change from an astronomical perspective, I will look more into this different perspective that astronomy offers, an almost philosophical one. And I think it's very interesting to see what astronomy has to offer in this climate crisis discussion that we of course all think about every now and then. And I think it's an extremely powerful perspective. So if the share screening is going well, let's assume that it is. I want to tell you a bit more about the story of the pale blue dot photo. And it's this maybe slightly unimpressive photo here on the left, but that had a huge impact on the way that we look at our planet and a huge impact on society altogether. So this photo is actually the last photo taken by the Voyager 1 spacecraft. And this spacecraft was then making its way into interstellar space. It was in the outer edges of our solar system and floating further and further away. So this journey started in 1977, when the Voyager 1 started from Earth and was shot out into the solar system, going to explore the outer planets for the first time. So it was the first probe that actually provided very detailed information about our two largest planets. So that's Jupiter and Saturn, in case you're wondering, and also some of their major moons. And this made it a very interesting scientific mission with a lot of interesting insights from an astronomical perspective. But that is not what most people remember Voyager 1 by. So this is the trajectory of Voyager 1. As you can see, it started in the center at Earth. And you can actually see two lines here, Voyager 1 and Voyager 2. Voyager 2 was actually launched first, but then Voyager 1 overtook it, and that's why they choose the naming. So launched in 1977, and then going out to the largest planets, to Jupiter and Saturn, which you can see, and then passing the orbits of Uranus and Neptune. And then you can see that in 1989, Voyager was passing Neptune and floating out into the edges. So already when Voyager 1 was at Saturn's orbit and passing the planet, Carl Sagan, one of the scientists on the project, proposed to take a photo of Earth, to turn the camera back around, instead of looking into outer space, look back at Earth and make a photo of our planet. Unfortunately, this was refused in the beginning, and that was done for very good reasons. Of course, it was not a photo that would have any scientific interest. It would not be able to resolve Earth. It would not be able to see any detail and in that way give us any real scientific information. But that was not the main argument. The main argument is simply that if they would take an image of Earth, the sun would be very close by, and the sunlight going into the camera might destroy the instruments for it not to be able to take any further data along the mission. So for the next 10 years, it was refused to get this photo, even though they always had it in the back of their mind. And then when Voyager 1 was finally passing Neptune's orbit and going so far away that the mission sort of had already completed, they accepted. They accepted on Valentine's Day in 1990 to take the photo. And so it was done. So they took a photo, they looked back at Earth and to the other planets in their solar system. And then even after taking that photo, it still took weeks and weeks for that data to reach us. once, because it just takes a long time for data to be transmitted back to Earth, but also because other missions were more important, so that data would come first. But then 1 or 2 months later, when all the data came back, this is what it looked like. This is what they also call the solar system family portrait. So what you see here is a mosaic, so a lot of different square photos of all the different planets in our solar system. A few are missing, either because they are too small or behind the sun, so not being able to see them with the camera. But you can see all of the major ones here. But of course, this is the one that we all talk about. Now, this looks a bit different from the one that I showed on the first slide. And that is because this year, this past February, the photo turned 30 years old. And due to that occasion, NASA has gone back and went through modern, updated versions of the data processing pipelines. And in this way, they got a new version of the photo. Now, first of all, you can see, of course, that this tiny dot appears in a band of light. And that makes the photo look almost magical, as if Earth is very special and the sun is shining down on it. But these bands of lights are not actual objects. They are what we call artifacts. It is caused by sunlight reflecting into the camera and the other parts, and therefore causing these lines that are not actually there. But that is what makes this photo look very special. And another thing to note is that we call this the pale blue dot, but it's technically not even a dot on this photo. It's less than a pixel big. And yet this pixel is what we call home. It's everything that we know. And I think it's interesting to know also why this dot is blue. And I think for a lot of people, they might assume that that's caused by the oceans on our Earth that are blue. And even though that contributes, that is actually not the biggest part. It is mostly caused by something that we call Rayleigh scattering. So of course, light consists out of all these different colors and wavelengths. And when they go through the atmosphere of Earth, blue is the light that is scattered more than the longer wavelengths, such as red. And that's why we see it as blue, that is so familiar to us. And then, when this photo was taken, Voyager 1 shut down its cameras forever. That was the last action it did. And I think it's very philosophical that the last action that a scientific mission of that size did was just looking back at Earth. When it's going out into space, what matters the most in the end is our own home planet. So in 2012, years and years later after that photo, Voyager 1 had made its way through the boundaries of our solar system and entered interstellar space. And now it is the most distant human-made object ever that's around, and it's still there, and it will keep floating away from us. Now, the reason that this image is so important and that it has made such an impact is not just because there's a dot that shows that we know is Earth. You don't even see it as Earth, you know it. The reason is described by Carl Sagan, who proposed to make the photo in a whole book. He wrote a whole book about it, and it's worth reading. But I think it all sort of boils down to this one quote from that book. And some of you may know it, that it's, "Look again at that dot. That's here, that's home. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known." Of course, that is not the only photo that we have of Earth. It's not the only photo where you can say, this is our home that we see. There's more photos that have done the same thing. And I think one of the first ones that did that was Earthrise. And it is from the Apollo 8 mission, where that was the first mission where we sent people to the moon in 68 already. So when these astronauts were in orbit, they saw the moon, and then suddenly they saw the Earth as well, rising from behind the horizon. And that is the photo that you see here on the right. And I've not turned this photo on its side. This is how the astronauts would originally see it. And of course, in most times that you see an image like this, they will turn it back around so that it feels like the way that we see the moon or the sun rising. But this is how you see it in space. And the reason why this is so important is that all these astronauts seeing this image describe that they have a change of how they see Earth when they see it for the first time in real life from outer space. They describe that when you see Earth, it suddenly looks so small. It only has a very, very thin layer of atmosphere to protect it from the hostile environment around it, you see that there are no national boundaries. All these countries and nations are human-made. They are not actually there. So when you see Earth from the outside, when you see it in the vastness of space, you suddenly realize that we are all on this planet together. And it is the only planet we have. It is the only home. Everything you know is there, and we have to protect it together. Now, this effect is called the overview effect. It resembles this change of perspective of how you see home. And this photo has been called the most influential environmental photograph ever taken. And I think that could well be true. Another one that I think is worth highlighting is The Day the Earth Smiled. This name is, of course, very poetic. What you see here is, again, this blue dot that is Earth, but through the rings of Saturn. That, of course, makes it a stunning image. The reason that they called it this is that it was one of the very few times when they actually scheduled the photo beforehand and also informed the general public about it. And then on the day that this photo would be taken, they asked everyone to look up at the sky and smile in celebration, all together under the same sky, reflecting on how we fit into the universe. So that is the pale blue dot message. That is what astronomy can tell us about Earth. And that is what it also has done. You can see that for each of these photos, and more of them, that whenever they were published and they came into the news, they spurred climate change movements. They motivated this feeling of standing together and acting together, and showing how vulnerable our planet is and the environment, and that we need to act to change that. And that is what we sometimes as astronomers call the cosmic perspective. It is a very, very powerful perspective, and the images that you see here are very well known. It's called the powers of 10. And what you can see in the bottom right corner is the skills that we all know. This is the scale that you grew up with when you're small. That is what you call familiar. And then if you go to the left, things become bigger and bigger. And when you grow up, you realize that you are not just part of your family and your home. You're part of a bigger city, a bigger region, a country. You start to learn about cultural values. But when you see yourself as a citizen of Earth, when you look at it from this cosmic perspective, you see that it goes beyond that. You see that if you zoom out even further, that these other countries, they are not so different than yours. We all have common values, and we all are in the basic pretty much the same. Then you go further out, and you see Earth as a whole, floating in space, with this tiny, tiny layer of atmosphere around it. And you realize that this is the only Earth. There are no other ones, and this is one that we need to protect. And then you go out into the largest scales of the universe, where you can't even comprehend anymore what the scales even are. And that is a very, very powerful perspective. So to answer Leah's question, can astronomy, even if we can't explain or change the way that climate works with our scientific facts, can astronomy still contribute to this discussion? And I think the answer to that is yes, because astronomy has a unique perspective on Earth, and therefore it can be used in a very unique way to invoke a feeling of global citizenship. Because these images, this perspective and this way of looking at Earth from the outside invokes a feeling of awe. It makes you feel small, it makes you feel humble towards our Earth that we need to protect. This can result in a feeling of global solidarity. And this global citizenship, as it's also said here by UNESCO, it is the sense that people are empowered to assume an active role, locally and globally, to building more peaceful, tolerant, inclusive and secure societies. And I would like to add sustainable societies as well. Even if we know with all the scientific facts how climate change works, if we know that we are the ones causing it, you won't act on it until you feel it. And you can feel it if you understand that what happens on either side of Earth is also impacting you. If you understand that if there's wildfires in Australia, and even if you live on a different continent, that affects you too. So seeing ourselves as this big spaceship Earth, as people call it, that we all live on together, that is, I think, the most powerful thing that you can have in education to make sure that people actually act on climate change. And of course, these photos, they started in 68, maybe even before. And we still haven't seen the change that we'd like to see. But astronomy can offer this to the discussion, and we should still all be trying to do that. So astronomers worldwide are trying to do exactly that. Of course, there's people researching the facts, and then there's those that try to educate with that try to do outreach and inspire people. So in the global level, we have this International Union of Astronomers, and they set up a flagship project that is celebrating our common humanity, exactly this pale blue dot perspective that Carl Sagan was already promoting so many years ago. So in this project, they want to use the beauty and moreover the scale of the universe to stimulate the sense of tolerance, common humanity, and global citizenship everywhere. And in the line of what I do, this field of astronomy for development, that is extremely important because it does contribute to development. If you don't have this basic idea of all standing together and being able to act on global challenges, it is very difficult to address challenges that are so big and so complex. So the International Astronomical Union set out all these activities worldwide. In February, when we had the 30th anniversary of this important photo. And all over the world, you saw small and bigger initiatives arising, discussing all these complex topics of climate change, but also how to be open-minded to other cultures through the lens of astronomy. And astronomy can do that because it inspires people. That is not just a nice thing. It makes it extremely powerful. People can come to your star party and just enjoy observing the night sky together and use that to start this conversation about climate and how we can play a role in that. So of course, in the Netherlands, we have been doing this as well. I am myself based in Leiden, and we organize a symposium around these topics. But more importantly, we will also be starting a project on a global scale to use these aspects of astronomy and to create this mindset in the future generation that we can all stand together. And we are targeting young children, especially because you are not talking about understanding the scales of the universe here. For young children, that might be quite difficult. We're talking about a more basic feeling of how do you value the people and the things that you see around you. And when you're young, that is when you're trying to form all that. That's when you learn how you see the people around you, how you see climate. And that is when you can have a tremendous impact on the way that they are now seeing the world and later acting on what they know. So of course, we have called this the Pale Blue Dot Project because it is the name that is most suited for something that tries to do this. And all in summary, it is about global citizenship and tolerance. And through that, raising awareness about how fragile our planet really is and what we can do about climate change and that we should do so. And of course, as any education project, we try to enthuse children about science and technology. Astronomy has a great potential to do that. But for us, that is almost a tertiary, well, quite literally here, actually, a tertiary objective. So that is the story of the Pale Blue Dot. That is what astronomy has to offer to this climate crisis discussion. And the perspective that Leo had to offer is a very scientific one. It's one that should show you how urgent this crisis really is. But the philosophical aspect is the one that I hope will incline you to really act on this and share the work. So thank you very much.
Thank you, Michelle. It was very interesting. Every time I see these pictures of Earth, I get chills. So I think, yeah, it's a very nice instrument to kind of, promote, right? As you said, to kind of get people thinking about Earth. So we have a question that is, can we get any science out of such kind of pale blue dot pictures?
So for some of them, we actually can. If they're from like the ones from the moon, you can actually see things in detail. Even so, I don't think they generally use them for any kind of science, because if you want to see, for example, if you want to see climate change happening, which you can do with satellite data, you can see how ice melts or how deserts change, but then you need to be closer up. And we can do that with satellites orbiting Earth. But when you go to these images from the rings of Saturn or all the way out to the edges of our solar system, they are not used for any kind of science. You cannot resolve Earth, so you cannot see any details. And in that sense, they would scientifically be deemed worthless. And that is why for most of these missions, they were not taken up into the original mission plan. And it took a lot of convincing to actually make them happen. I think in the Voyager 1 mission, a lot of people thought, why would we do this? Why would you want to see this 1 pixel of Earth when we already know what it's going to look like? And even though there's no scientific merit, in the end, it's turned out that there is a real impact of this. And I think it's a great thing that these photos were made.
Yeah, I completely agree. So then we have a question. Could all these pictures be fake?
I suppose they could be. I suppose all of climate could be a hoax. I prefer to believe not.
But then again, we also saw movies from 60s, right, as well. So they kind of don't look as well as Pale Blue Dot.
Exactly. It would take a whole lot of effort and money to make this fake.
Yeah. So then we have a question also. Do you think the field of astronomy should play a more active role in promoting this global citizenship?
Yes, I do think so. And mostly because we talk about climate change as if, it's happening and astronomy is only playing a role in observing it. But I don't think that's true. As Leo was explaining in his talk, this is really a crisis. It's urgent. We already knew decades ago that it's happening, and it's happening fast. And I think everyone who can play a role should do so. And we know that in astronomy, a lot of researchers are very active in talking to the general public, in giving talks at schools, for example. And I think every astronomer can try to include this perspective and spread the word about it. So yeah, I think there could be done more, and whenever it should be happening.
Is there also maybe some kind of help? For example, if somebody wants to do some kind of outreach project, can they just contact you, for example?
Of course, they can contact me. I mean, of course, by now I know quite a few things about this, but there is more sort of global help for this. Both Leo and I are a member of this international group called Astronomers for Planet Earth, which started in the US. And then in Europe, we also had these conversations about sustainability and climate and what astronomy could do. And we heard about this bigger group in the US, and now it's really becoming a global movement. So if you go to their website, they have a lot of educational materials. You can join the group and be part of the discussion if you want to know more. So yes, there's definitely a lot more out there to help.
Can you just repeat the website or the name so that...
Astronomers for Planet Earth.
Okay, that's interesting. Then we have, would detecting life elsewhere have any effect on this perspective of Earth, in your opinion?
I think it would, of course. But part of this perspective is the feeling that we are all alone out there. The fact that you see our tiny, tiny Earth floating around in empty space and there's nothing around it. So observing life elsewhere would change that perspective a little bit. Although on the other hand, it might also emphasize that life is, if it's out there, it's so far away, we will never be able to travel there. So it might also emphasize that even though we might not be alone, we have no other opportunity.
Yeah, but as well, we kind of, but in which way, actually, would you think that it would change the perspective kind of people, like positive or negative more?
I think people would be very excited in the beginning, right? That would be the ultimate sci-fi story. But if you look at, people's tendency to think of themselves as very important, the universe still allows us to do that. We still are the only planet with life on it, and that is still a very special position.
Yes.
If we would detect life outside, we would not be like on our throne anymore. So I think in the end, it might even have negative implications.
Okay. I thought okay, maybe it's then positive because we finally think, okay, there is somebody else and they're maybe doing better than we do. But
I think people would be scared of that if they're doing better than we do.
Yeah. Okay, we have more questions, but we will continue the discussion. So after the pub quiz, when you can all join us live, as we said. So we will put a link that you can all click. So now let's virtually thank Michelle again.
I look forward to talking to you in the live chat.
And then also, so we will have a little break with the Kahoot link, so you can all join, and we'll see you in approximately 3 to 5 minutes.
Hi guys, so we will start the quiz in 3 or 4 more minutes. Our prize, as usual, will be a €25 gift voucher to Buckshot as soon as they're open and have customers again. So I strongly encourage you to join the quiz. I'll keep sharing the link. All right, we're getting ready to start the quiz. And I'll give a few more minutes for anyone else who's left to join and come on into the quiz. But then we'll just be in quiz time. So if you've played Kahoots with us before, you know that the faster you answer, the more points you get. And if you're getting the right answer is also helpful. So fast right answers do better. Also, just because we're doing this through Zoom, there's a bit of a lag between when I ask the question, when you see the question on the screen, and when the question's going to close. So we have all the questions set for 60 seconds. But if you wait until second number 60 before you answer, you're going to be in a bit of trouble possibly about getting that done. So let's get ready to start the quiz. So I'll give you about 30 more seconds in case anyone else wants to join, and then we'll be getting into the quiz just as soon as we possibly can. Pub quiz for May 2020. When viewed from beyond the orbit of Neptune, Earth as a bright yellow spot, a faint green blot, a variable purple knot, or a pale blue dot. Good job, guys. A pale blue dot. Next question coming up. The best at the top, proving their name, I guess. Let's see how things go. What are Milankovitch cycles? Special bikes that work both on normal bike paths and on water. Long-term changes in the Earth's climate due to orbital changes. Changes in fashion observed especially among young scientists, or a fancy name for the motion of pinwheels. Either the minute runs out or all the teams answer. All the teams answer. Yes, and all the teams got it right. All the guys got it right. So there we go. This quiz, we have just one round for a change. So everything's to play for right in this first round based on the talks that you heard today. And by the way, at the end, if you're in a winning position, you need to take us a screenshot of your winning screen on your phone and send it to us at aotgroningen@gmail.com, and then we'll know you're the prize winner who should get the €25 voucher. But just make sure you take that screenshot of being the winner, unless we can tell that it's really you from your name, but who knows who the best is. Question 3, what are sunspots? Tiny patches of pigment on the skin after receiving too much sunlight. Bright little points seen on the ground when the sun shines through a tree. Hotter regions on the sun's surface or colder regions on the sun's surface. Hotter region on the sun's surface also popular, but really depends how you define temperature in this situation. So come join us after the end of the quiz and have an argument with Leo about which you think is really right, if you want to have that argument. Oh, things have changed place. Boo is getting up there. Peter has a streak with 3 correct answers. So let's see what's next. What is the name of the closest known planet from our solar system? Deep Space Nine, Tatooine, Proxima Centauri b, or Alderaan? Correct, everyone. We all know Alderaan was blown up a long time ago in a galaxy far away. Again, where Tatooine is sitting, and Deep Space Nine is just a space station, not a planet, not even a moon-sized space station, like some people build. Yeah, Proxima Centauri b is the closest planet that we know about. The best, getting back up there. Which space mission produced the pale blue? Cassini-Huygens, Vostok 1, Voyager 1, or Apollo 11? Voyager 1. Correct. See how we did on the speed of those answers. Yeah, the best clinging on, but everyone still in the running, I think, for this inaugural online live quiz. What is the cognitive shift in awareness reported by astronauts looking at Earth from outer space? The overview effect, the cosmic perspective, the cosmic zoom, or global citizenship? Overview effect, when you can see that whole planet at the same time. Cosmic perspective, also a good phase. And we should all have global citizenship, but not the psychological effect that astronauts get. let's carry on. The best on a streak, but Tamo 80 shooting up there. See how this goes. Now the next questions are going to be quotes from Carl Sagan. And this is true or false round. Did Carl Sagan these quotes or not? Number one. The Earth is a very small stage in a vast cosmic arena. True or false? It is indeed a Sagan quote. Pretty split on that answer there. Oh, Tamo 80 getting up there. Peter getting up there. The best. Can you still be the best by the end? Number 9 of 11. The delusion that we have some privileged position in the universe is challenged by this point of pale light. Did Carl Sagan say it? Yes or no? A Sagan quote. So unfortunate, the majority of you didn't think so, but so it is. Let's see how we go. Number 10 out of 11 we're getting to next. Peter taking over Tamo 80. The best still in the running. I think probably lots of other people are in the running still with the last 2 questions. Remember to look up at the stars and not down at your feet. Did Sagan say this? False. Good job. I think maybe you're just all saying false now, just in case one of them was false. See how things are going. Last question, and it's looking like maybe an unsurmountable lead. Let's see how this goes. Question 11. Science is not only compatible with spirituality, it's a profound source of spirituality. It was true. And let's see if that has shifted the scores around. Here's the podium. If you've got one of the top 3 positions, please take a screenshot and send it to us. First position will get a €25 voucher for next time we're back at Buckshot as soon as it opens. And second and third place, as soon as we can get our posters and stickers, you can come get them from Buckshot too. So screenshot your phone if you're one of these winners up here. Congratulations to Peter. Second, congratulations to the best. Third, congratulations to Boo. So, thanks for taking part in the quiz. And I'm now going to share the link so that you can all come join us in the Zoom and all take part together. We can ask Leo and Michelle questions, meet any of the team from the Astronomy on Tap Groningen, and do all of that. So the link is http:// AoT Go, all in uppercase letters. And I'm just going to share that on the screen now. Then we'll share it in social media because this stream will end in about 3 or 4 minutes, but I'll start letting you in the room as soon as I can. So hope to see you in a minute, and congratulations again to those quiz winners.
Now? Okay, they cannot hear us on YouTube.
I can still not start my video, by the way.
Sorry, you can still?
I cannot start my video.
Oh, but they can hear us on YouTube.
Okay.
Yes. Is it working?
Yeah.
It is.
Hello.
That's just a delay of 10 seconds.
Maybe.
Hey guys.
Love the sound.
Is this all the AoT Groningen team now?
There are a lot more. So I think they will also all join. Not sure what is happening with Willek.
Can you tell Jake to stop the video? The music is...
Yeah, it would be nice, but I will send him a message. I know.
I stopped the music now, but I'm going to stop the screen in one more cycle through the music, I said, but you can't hear me because the music was playing.
Okay, because we were heard on YouTube as well.
Yeah, probably.
Okay, yeah. So maybe still. Is it still? Yes, it's still. Hi, everybody on YouTube.
I'm just going to put the music for 1 more minute and then we'll stop sharing it. So turn it off if you don't like it. You'll see when it changes.